Welcome to lecture number 9 of the course Industrial Engineering. The topic is design of assembly lines and line balancing. In this topic, we will study the concept of assembly lines and line balancing, the methods of line balancing with an example. So first we will see what is the meaning of an assembly line. An assembly line in a production system in which the product moves through a series of workstations. A specific task or group of tasks is performed at each workstation. So workstation means what? It can be a machine or a group of machines, and the product will move through these workstations. Workstations are arranged according to the sequence of operations. The product is progressively assembled and it moves along the line. It is generally suitable for high volume standardized production. Examples of assembly lines are given here: automobile assembly, electronic products, home appliances, etc. One example of an assembly line is shown here. Input can be raw materials or a semi-finished product for a particular assembly line. Then it will go to workstation 1, then workstation 2, workstation 3, workstation 4, etc. like that. Then it will come out as a finished product. In the case of automobile assembly line, the parts going to the next workstation, first workstation is frame assembly, then to the next workstation, that is motor installation, then to the next workstation where wiring is done, then the next workstation inspection, then it will come out as the finished product. So an automobile workstation is shown here. These are the parts for this particular assembly line. There may be many assembly lines in an automobile factory, but this is a particular assembly line. Here parts like wheel, seat, door, engine, battery, etc. are the parts. Then frame is there. That frame is already made from some other assembly line. In that frame, in the next workstation, that is motor installation, we can see engines are installed. Engine is installed, then other parts, then wiring. Wiring is required for a car. So wiring is done in the next workstation. Then inspection is done at the next workstation. Then the finished product, that is a full-fledged car, comes out from as a finished product. So we can see part by part the product moves from one workstation to the next and is transformed into a finished product. So this is an example of a typical assembly line. Why we need an assembly line or need for assembly line design? The answer is this: a properly designed assembly line should ensure smooth flow of work, reduce waiting time and idle time. If the assembly line is not designed properly, then there will be waiting time in each workstation and idle time for a particular machine or workstation will be higher. Then the next point is avoid overloading individual workstations, achieve the required production rate, utilize workers and equipment effectively, minimize the number of workstations, reduce production cost. So these are the need. These points shows that assembly lines are important in a production facility. So to ensure these type of things like ensure smooth flow, to reduce production cost, ultimately to reduce production cost, we need to design assembly line properly. So that is known as line balancing. So this leads naturally to the concept of line balancing. So what is line balancing? That is the next question. Line balancing is concerned with the assignment of various work elements or tasks to different workstations so that work is distributed as evenly as possible. The required production rate is achieved. Idle time at workstations minimized. So line balancing means assignment of various work elements or task. What is a work element or task? That we will see in the next slide. So assignment of various work elements or tasks to different workstations is known as line balancing. So simply we can say unequal work distribution, if it is there, then idle time will be there, so that will lead to lower efficiency. If balanced work distribution is there, then less idle time and higher efficiency. Okay, so why is line balancing necessary? It is explained with an example here. Workstation names are given here. Workstation 1 WS1, Workstation 2 WS2, Workstation 3 WS3 and Workstation 4 WS4. Work time in each workstation is shown here. 50 second, 25 second, 45 second and 20 second for each workstations. If the line, that is assembly line, if the line operates according to the slowest station, then cycle time means the time required to complete the work, will be equal to 50 seconds, because the slowest workstation here is the workstation 1 with the 50 seconds. So that will decide the cycle time. So 50 seconds is the cycle time. Then workstation 2 and workstation 4. Workstation 2 has 25 seconds and workstation 4 has 20 seconds. Will remain idle for substantial periods, because those workstations need only for 25 seconds and 20 seconds respectively to complete a work. But since the workstation 1 is required 50 seconds time, these workstations or WS2 and WS4 will remain idle for substantial periods. So that will give an unbalanced production line. Unbalanced production line means less efficiency, less productivity. So here an unbalanced production line and balanced production line, that is unbalanced assembly line and balanced assembly line, is shown here. So here workstation 1 is this and workstation 2 is this. Workstation means there can be one or more machines. So here this workstation having 50-second cycle time. So when the input comes to this workstation, it will always be working because it is the first workstation and it has to complete the work in 50 seconds. So it is always busy. While it is working on this input, the next workstation, workstation 2, is waiting for finished product from workstation 1. So the operator in workstation 2 is waiting, and workstation 3 is mostly busy because here also the cycle time is high, that is 45 seconds. So the worker, the operator there is working most of the time, so mostly busy. When he is working, we can see the next workstation, which is having a less cycle time or least cycle time, 20 seconds, is waiting for workstation 3 to finish its work. Okay, so 2 are busy and 2 are waiting. So this is an unbalanced assembly line. But if you distribute the cycle time for each workstation in such a way that shown in figure below, then all the workstations will become busy. All the workstation operators will become busy. So here workstation 1's cycle time is 36 seconds, workstation 2 is 34 seconds, workstation 3 is 35 seconds and workstation 4 35 seconds. So here not much difference in cycle times. So all are busy. So cycle time here is 36 seconds. That means the cycle time for the highest work cycle workstation, that is 36 seconds. But in the above figure, cycle time is 50 seconds, that is for the highest work cycle time for workstation 1. Okay, so how this can be achieved? How we can change the 50-second cycle time to 36-second cycle time? That is what we are going to explain in line balancing methods. So the aim of line balancing is obtain an optimum or most promising balance that is done to improve the flow of production or assembly process. Group task so that the total time is preferably equal to the available time at each workstation or slightly less than the available time. So that will reduce idle time. So the aim of line balancing aims at grouping facilities or tasks and workers efficiently so that we will get a balanced assembly line. So balanced workload will give minimum idle time and improved productivity and production flow. So how we can achieve this? That we will study in methods of line balancing. There are many methods of line balancing: heuristic method, linear programming method, etc. For intermittent flow systems, heuristic method of line balancing is normally preferred because they are simple, less time consuming and less expensive. So in this topic we will be studying only about heuristic method of line balancing. Dynamic programming or linear programming line balancing will be taught in another topic. So heuristic method of line balancing. The heuristic method involves drawing a precedence diagram first, then identifying the feasibility of transferring tasks laterally from one column to another, then obtaining a satisfactory line balance. This line balancing method of heuristic method will be explained with an example. So before going to the example, the procedure steps are shown here. Step 1, identifying the work or job. Then break down the work into elemental tasks or steps. For example, drilling a hole can be considered as a step or elemental task. That's the meaning of a step or elemental task. That is the smallest step in the assembly line or in the work. Then in step 3, we will list elemental task, their immediate predecessors and duration of each task. Then we will draw the precedence diagram and indicate task duration on each step or task. So before going to the example problem, we will study some of the important terms in line balancing. First one is task bar work element. A small unit of work required to complete the product is known as a task. For example, drilling a hole. That is an example of a task. The time required for that particular task is known as task time. Time required to perform a particular task. Workstation. A location where one or more tasks are performed is known as a workstation. A workstation can be a single machine or more than one machines. For example, in a workstation, sometimes there will be only a lathe. Sometimes there will be lathe plus drilling machine plus grinding machines. So in workstation can be a single machine or a combination of machines. Precedence relationship, that means the required sequence in which task must be performed, that is known as precedence relationship. For example, work 2 should be completed before 3 is started, like that. Work B should be completed before work F is started. So this kind of relationship is there for drawing a precedence diagram or a network diagram, that is known as precedence relationship. Cycle time. Cycle time means maximum time available at each workstation to complete its assigned task. That is known as cycle time. So don't confuse cycle time and task time. Task time is for a particular task. Cycle time is for a particular workstation. In a workstation, there may be many tasks. So, for example, cycle time for a particular workstation is 10 minutes, means if there are 3 machines, then machine 1 plus machine 2 plus machine 3 equal to 10 minutes. Now we will see an example problem for line balancing heuristic method. So this is the example. Here 9 tasks are there in this production line. So tasks are given in the first column. Their immediate predecessor are shown in the second column. Then duration of each activity or each task is shown in the third column. Duration is in minutes. So 1 and 2 has no predecessor. That means 1 and 2 can be started first, simultaneously or at different times. 3 should be started only after 1 is completed. 4 should be started only after 2 is completed. Like that, 8 should be started after 6 is completed. And the last task 9 should be started only after 8 is completed. So that is known as precedence relationship. Now we will draw the precedence diagram or network diagram. Here the completed network diagram is shown here. 1 and 2 has no predecessor, so that 2 are started first. 1, 2. On 1 and 2 we can see 3 and 4. Those are the durations in minutes. So 3 and 4. Then the next task is 3. So before 3, 1 should be completed. That means from after 1, 3 is started. So from 1 to 3 there is an arrow. That means after 1, 3 is started. Then 4. What is the precedence task of 4? That is 2. That means after 2, 4 should be started. So from 2, after 2, 4 is started. So draw a arrow from 2 to 4. That means after 2, 4 is started. The timing duration of 3 and 4, that is 2 and 5 respectively, are shown above the circle. Then 5 is here. What is the task before 5? That is 3. So from 3, after completing 3, 5 is started. So draw a diagram, draw an arrow from 3 to 5 with 4 as the duration. The next task is 6. So 6 is after 5. So after 5, 6 is started. So draw an arrow from 5 to 6 and duration above 6. Then 7, the precedence is 4. That means that is here. 4 is here. From 4, 7. After 4, 7 is started. That is the meaning of this. From arrow from 4 to 7. 2 is the duration. 2. Then 8. 8 is after 6. So from 6, draw an arrow, then 8. Then the last activity is 9. 9 should be started after 8 is completed. So from 8, draw an arrow to 9. So 9 is the last activity. Then complete the network diagram by drawing a an arrow from 7 to 9. So 7, after 7 only 9 should be started. That is the meaning of this. Okay, that is understood. So this is the precedence diagram. So the precedence diagram shows the sequence in which the task must be performed. So the numbers in circles are the task numbers. Numbers above that are task duration in time units. Here it is in minutes. So the precedence diagram helps in determining the feasible sequence of task. So this is precedence diagram. We have drawn that. Now, in our example, it is given that total task time equal to 38 minutes. Then cycle time is given as 10 minutes. Cycle time means time required to complete a particular workstation or task in a particular workstation. So total task time 38 minutes, cycle time 10 minutes. So dividing 38 by 10 we will get 3.8. That means minimum number of workstations required equal to 3.8. We can write it as 4 by the nearest integer is 4. So 4 workstations are the minimum number of workstations required to complete this task. In each workstation there will be more than one machine or only one machine. Okay, but the maximum number of stations can be as many as the number of individual tasks. How many individual tasks are there? That is 9. So maximum 9 workstations are possible. But the aim is to achieve the balance using 4 workstations. If the number of workstations are less, then that will give more productivity. So we will try to keep the minimum number of workstations, that is 4. So we'll see how we will achieve that from the precedence diagram. So we have to assign task to each workstation. So the first step is permutability of task. Task from a number of steps, columns can be combined to bring the total time closer to the cycle time, provided total time does not exceed cycle time. Precedence constraints are maintained. That means we can combine 2 or more tasks, but the cycle time, that is 10 minutes in this case, should not be exceeded, and the precedence constraints given in the precedence diagram should be maintained. Then another way is lateral transferability of task. To make the total task time equal to cycle time, task may be shifted laterally, provided precedence relationships are maintained. We will see in this example how it is achieved. So using the two concepts given, so column 1, 2, 3, 4 and 5. This is as shown in the precedence diagram. Here 1 and 2 are this, then 3. We will combine 1, 2 and 3 tasks. Then we will combine 5 and 6 tasks. 1, 2 and 3 combined together, that is the workstation 1. So when we combine 1, 2 and 3, we should check how much is the cycle time for that particular workstation. 4 plus 3, 7 plus 2, that is 9. So that is less than 10. So these 3 can be combined into a workstation. So this is number 1 workstation. I will write here as 1. Now 5 and 4 is combined. 5 task time is 4 and for 4 task time is 5. So 5 plus 4 is 9. Still it is less than 10. So 5 and 4 is the next workstation, that is workstation number 2. Then 6 and 7. 6 and 7 are combined as workstation number 3. The tasks are 8 plus 2, that is 10. So that is possible. So this is the third workstation. Then 8, 9, 9 combined as the fourth workstation with the 4 plus 5, 9 as the cycle time. So 4 workstations are ready now. So they are named as SA, SB, SC, SD. So here how it is done, that is explained. For station A or workstation 1, the tasks are 1 plus 2 plus 3. Total time is for each is, for 1 it is 3, 2 it is 4, and 3 it is 2. So total time is 9 minutes. So that is less than 10. So then what is the ideal time in that workstation? 10 minus 9, that is 1 minute. Okay, the workstation will work for 10 minutes, but total task will be completed in 9 minutes. So 1 minute ideal time is there. Then station B, that is the second workstation, 2 tasks 4 and 5. So 4 plus 5 is 4 plus 5 means 5 and 4 are the timings of the work task in those workstations. So 5 plus 4 is 9, that is less than 10. So ideal time here is 10 minus 9, that is 1 minute. Then station 3, we have combined 6 and 7, and the timings are 8 and 2. So 8 plus 2 is 10 minutes. Here ideal time is 0 because 10 minutes, and the workstation cycle time, the constraint here is cycle time is 10 minutes. So 10 minus 10 0. And for station D, 2 tasks are combined, that is 8 and 9. So their timings 4 and 6, 4 plus 6 equal to 10 minutes. So ideal time equal to 0. So if we combine in this way, the ideal times are minimum. So here what is the total ideal time? Here 1 minute, here 1 minute. Then the other workstation say workstation A 1 minute, workstation B 1 minute, workstation C and D 0. So total ideal time is only 2 minutes. So we can proceed with this kind of arrangement. That means combining task 1, 2 and 3 and make it as a single workstation. There may be 3 machines. In workstation B, we are combining 4 and 5. For example, it may be painting and grinding. Those are combined together in a single workstation. Maybe these two are using 2 machines. Then we will get only 1 minute ideal time. Then in workstation C, 6 and 7 tasks are compliant. In workstation D, 8 and 9 tasks are compliant. So this is the method of line balancing, and this method is known as heuristic method of line balancing. So this is the topic. The topic assembly line and line balancing is completed. So to subscribe this channel, click on the logo on top right corner. We will see in the next topic. Thank you. The different stations A, B, C, D and the task assigned to them, work time in each workstations and the idle time are shown here. So the total ideal time equal to 2 minutes per cycle.